first and more important one will be to show how to approximate a function more or less by compactly supported measure by multiplying with a huge plateau function. But I will produce these plateau functions by using what I call BUPUs. It's a funny name for bounded uniform partitions of unity, and you just see one of these BUPUs here. It's just a very simple way, very much like in the spirit of spline function theory or differential geometry, where people would say, I have a function on the manifold. Locally, the manifold is like R2, so I cut it into pieces and move them into the Euclidean space, and I have to glue them back or so. I'm just also trying to cut everything into little pieces. And actually, what I will do is to do refined partitions of unity. So it will be in the Euclidean space very easy to have fine partitions of unity. I mean, if you look at this picture, somehow this orange guy is going from here to here. So it has a support. And the next one has a support of equal size. In this case, in my terminology, is a regular BUPU or a shift invariant system obtained, which is one function shifted around, but with the extra property that it's adding up to 1. So the thing that I'm using very often as a standard example is the system of triangular function. So you have a triangular function from -1 to 0 down to 0 to +1. The next one is starting at 0, and if you add them up, of course, you get constant 1. So essentially, you could say, if you think in terms of splines, this is a spline of degree 1 of order 2. You need 2 coefficients, and it adds up to 1. If you convolve the triangular function with the box function, you get a quadratic spline. Or if you take it 4 times, or you convolve triangular function by itself, you get a cubic spline. That's more or less what you see here, except that if you do it in this way, then these building blocks are getting broader and broader. So sometimes you would say, well, if I convolve a rectangular function 4 times, but I don't want to have the support being bigger, then I take the big original the rectangular function, which is kind of okay with the translation parameter that I have here. And then I smooth it with more narrow functions. Maybe it's better to not smooth only 3 times, but maybe 5 times, but with a smaller rectangular function. So in this way, we can produce many different partitions of unity. And our MATLAB command, which is really doing exactly what I was mentioning in the discrete setting using FFTs. One of my students was doing this. Is called BUPU spline. Total signal length is 256. Gap size, or how much shift parameter offset you have, is 64. The basis is, the broadening is how much you do extra smoothing or so, is 16. And we apply 4 times the convolution. So this function will be probably 4 times differentiable. The support size will be the original 64 plus 4 times 16, which is each time I convolve, it's broadened by so much. So I would guess it should be 128, which I think is realistic, because if I take the support of the red guy, it goes more or less to the middle, and then the violet guy is taking the second part. So in this way, I have something which is not too bad. And I just played a little bit around to doing some other ones. So that would be kind of a partition of unity in the trivial sense of just having box functions. I was choosing, I think, 3 times and only 3 things. So the smearing relative here is only 6 pixels. You see signal length is now 480. And whenever I'm thinking that I'm using a partition of unity, you should think that maybe in the extreme case, it's a collection of rectangular functions. For me, because of my setup, I'm not allowed to apply my functional to a rectangular function. Of course, you can apply a measure to an interval or so. But if you think of these rectangular functions being a little bit smoothed, you have already very good ideas of what happens. Another thing which will come up later, and where such a picture may be helpful, is a histogram. So you are saying something is normal distributed or so, so some quality or so. So you have a large number of data, and then how do you look at the data? You produce a histogram. because you are not automatically getting the probability distribution, but you're looking how much was there in this bin. And for me, in this setting, it will be apply the measure to these individual pieces, which add up to 1, and then you know how the mass distribution is. So knowing the measure on these things is more or less like knowing a histogram. That's why it's plausible if I make the histograms finer and finer, eventually I get the measure. I will do it in an appropriate way. Now, maybe another thing is, this is, so to say, one of the standard things that we are using. This is cubic spline. So kind of that's the standard. If I just tell you I want to have a spline, a spline bupu of total size n, 480, and with gap size, I think A is 20, so I have 24 building blocks if I remember correctly, then it would do cubic things. But you also would say, it doesn't look so different from how I think a Gauss function looks like. And then I said, yes, you're right, that's the beginning of central limit theorem. If you do convolutions more and more, the shape will be more Gauss-like. So the point is, Gauss is not good if you think it should be rectangular or it should be plateau. If you have plateau-like partitions of unity, you are more in the spirit of histogram, so it's more plausible, but it really doesn't matter. We will play a lot with these partitions of unity, which are then later on going to 0 in the definition. Now let me see. I was checking in my notes. There are 2 pictures which are typical for engineering textbooks. Maybe I should redo this because I'm used to have complex valued functions. Therefore, you see 2 functions, the real part, the imaginary part of some band limited signal. So I was trying to take a function which is not too bad, too rough. So I was choosing a band limited function, which simply means I was taking random Fourier coefficients in a certain range. I mean, I was defining a sequence with some random numbers. I was taking the inverse Fourier transform. But in order to make it decay at the end, so to give you the impression I'm showing you something on the real line or so, I was, of course, multiplying it with a partial sum of my bupus or with some plateau functions to damp it a little bit. Now, engineering application, explanation of translation invariant system behavior, and with the spirit of going towards the impulse response, is to say, well, it's clear from the picture that this green step function is convergent to the green function. But the step function is a sum of shifted copies of the original function. Therefore, if I know what these rectangular functions are on the output side, I can expect to know what the output is because I can write everything and pull the shift parameter through. Now, then the explanation becomes a little bit tricky, and I usually don't consider the limit. One is, I would say, I mean, how do you choose the height of the step function? If I remember correctly, I even don't know it for sure, I was really choosing the L2 projection. So I was doing the mean value over each of the intervals, which is the best approximation in the L2 sense. So, okay, then I would be able to claim I have done a good approximation in the L2 sense. But do they write that the operator is continuous in the L2 sense? So something that is approximated in the L2 sense would have a good approximation on the output side? I have not seen such conditions. If they say we are approximating in the uniform sense, it's also not good enough or so. So that's why I think we should just a little bit twist the perspective and say, well, I think it would be completely in the spirit of engineers that we are saying we are trying to use a piecewise linear interpolation, or actually, yeah, that's not piecewise linear interpolation, but we are doing what I will call a spline approximation operator. So that's kind of, in the case of triangular function, it is a piecewise linear information. So essentially what I'm saying is I'm trying to approximate the given function by a sum of shifted functions. These will be the elements of my bupu. And I make these functions continuous. And the point is, if you're familiar with Sobolev spaces or so, if somebody is giving me 3 times differentiable functions, I will guarantee you that the convergence is also not including the only level 2 norm, but in the Sobolev norm or so. So if somebody is giving me a decent thing, then I can hope, knowing the output of these elements, I can do things. Second point is, usually they make some experiment or they show that if you put rectangular functions, the output will finally stabilize, and they call this the impulse response. We will do it maybe with weak star arguments or so, then it's well settled or so. But in the standard explanation of engineers, I would say, okay, I can take the rectangular function and I can take the Gauss function. So why don't I have a rectangular shaped Dirac function and the Gauss shaped Dirac function and the triangular shaped Dirac function? So why is the integral is preserved in the limit, hopefully or reportedly. Why is the shape also, why is the not preserved also? And we will do something like this. Okay, so there are 2 things which I have to do now. One is to explain you how to use these things, and just because it pops up first, I try to tell you that the key point is really this equation number 43 now. So we have seen this partition of unity, and we think that later on we will make these partitions finer and finer. So, but what we will do is we will say that the norm of the measure is the sum of the norm of these pieces. So kind of essentially we cut the measure into little pieces, but the norm of the total thing is the same as the norm of the measure. And for me, this property is exactly the exact analog of the sigma additivity property. So if I would take a partition of unity, which is just indicator functions of sets, so practically I would say, if you take a rectangular function here and make a partition of unity in this way, then to say that the measure of the first interval plus the measure of the second interval adds up to the measure of the real line, and that's more or less the equivalent of this functional norm, then you can understand why continuity of the functional is what you can use and what you should use for the proof here, and what we'll pull out from this. And we will see very quickly how it's related to properties of C0. So C0 is a harmless function space. The norm has some extra properties compared to other function spaces. And I will try to show this first, because in this way we can also see all the definitions that we need. And this is really, kind of clearly, if this sum is absolutely convergent, because the sum is some finite number, then I can take finite partial sums, and that means I take all the important pieces where the rest of the summand is smaller than epsilon, and I have already my approximation, which then finishes the proof of the other one. Okay, so the first thing is, if you give me, well, let's see. No, I think, sorry, I'm in the wrong. Here I'm using it and not I have to check. Sorry, that's not so good here. Yeah, that's the correct theorem now. So theorem number 4 is saying, if somebody is giving me a partition of unity, normally it doesn't have to be non-negative, but for convenience I'm putting a non-negative, then the sum of the pieces measured individually is the same as the norm of this functional. And the consequence is that the series is absolutely convergent, and that means that it's unconditionally convergent. So of course, only countably many terms can be non-zero, and you can enumerate them, but it doesn't matter in which order you do the enumeration. Actually, my way of viewing is I can take the net of finite subsets of my index set and say if you have enough of these sets, the rest is arbitrary. But that's not so important. Okay, the first thing is, of course, we are living in a dual space. The measures are the dual of C0, and we have heard the dual space of any normed space or of a Banach space is itself a Banach space. And in any Banach space, an absolutely convergent series is convergent. So the only thing that is maybe missing in this explanation is that is it really adding up to the right measure? So you have to say, well, what if I add all these mu psi's to some f? And then, of course, you could say, well, what does it mean? Well, look at all the values mu applied to psi I psi. And I'm saying, okay, it's clear. F equals f times 1, and 1 is the sum of the psi I. So the partition of unity is just telling me that this is really in the sense of strong operator topology, or in the sense of ordinary convergence, it's okay. But is it absolutely convergent? This is something we have to check. And now the opposite is kind of, I had a very or rather involved elementary proof, but then it turned out it's not so difficult to both explain what's going on and go through the proof. So first of all, we remember that the definition of the norm of a functional is you take the sup over all the elements of your Banach space of the absolute value of the functional here. That's kind of the definition of the norm. Now, what is clear, if you think for a moment, is that if you're replacing the f, which are arbitrary C0 functions, by some elements from a dense subspace, it's also okay. So you can always think, because you split your epsilon to some 3 epsilon or so, that you can find not only a function in C0, but even in compactly supported. I'm not sure if I will need it, but let's say we do it. Yeah, what we want to show, what we want to show is that this sup cannot be strictly, the measure norm, where are we here? The measure norm cannot be really less than things. So we want to have knowledge of the pieces and want to show that they are close to the norm of the function. Now again, what we have is we have lots of pieces. All these local measures have a certain property. And maybe we think of the real line and we put numbers 1, 2, 3, or minus k to plus k and so on, and we count all of them. Each of these local measures, now we fix the index, we have some error. You can imagine that I have infinitely many errors, and altogether they should not hurt. So I take a sequence of epsilon I such that the sum is also very small. So I split my epsilon into a sequence of epsilon I. So maybe you say, for the first epsilon, let's say it's 0, I take epsilon over 2. The next one is epsilon over 4, epsilon over 8, epsilon 9. I take any enumeration. So here it's just a family of those terms, and I make this. Now, for every mu I psi I can find, by the definition of the sup norm, I can find some function f. Yeah, this is in C0, which is in the unit norm. So I can a function which responds almost like the operator norm or the functional norm to this. So there, at every point, there is a function responding very sensitively, so that mu psi I applied to fi, which in reality is mu applied to psi I times fi, is larger than the worst case, which is this here, up to some error, but this error is very small. Now, what we have is, when we look at the action of this thing, is that it might be complex valued or so. But we can, of course, change the function f so that it's a real valued thing. So that's kind of a good trick to say that we can assume that the mu psi, these values, we don't care about the absolute values. Now, if we have a finite set of functions, a finite set of indices, so somehow the idea is now I'm caring for the relevant points. Most of the sum of these things is at some finite set. I can always define a function gluing together these pieces. So what is the general problem? I'm watching what is happening here. My psi number 5 is located here. But my f with number 5 is something which may be somewhere. But that should not be relevant because this may be difficult when I glue it together. But I want to just take the part which is belonging here. So the f with number 5 is put together with the bump function number 5. Maybe I use this here. Yeah, that's okay. Yeah, okay. Yeah, there is a pointer. Oh, thank you. Thank you. Good idea. Okay, so the trick is, on the one hand, I want to avoid discussions about convergence. Therefore, I'm saying take a finite sum. On the other hand, I'm saying, well, we will choose this finite sum later, so it's whatever you're doing, you get this here. Now, what can you say about, I mean, again, choosing a finite set, and we think a sufficiently large but still finite set, we want to see what the action of M is on that F. And now, of course, F is the sum of the pieces. But M applied to psi Fi is really M applied to this here, which by the arrangement here is the maximal effect that you can have up to some epsilon I. But all these epsilon I, if you subtract them together, now I take the sum of all of them, is still at most epsilon. And so you see that we can always find, if we take this set sufficiently large that this finite sum is less than epsilon, then we're done. And the other situation, which maybe I should not even discuss in detail, I mean, how do we know the sum is finite? Well, it could be infinite. Well, that means we can take a finite set such that our measure is arbitrarily large, but that's also not possible. So kind of, if it would be infinite, we have an even easier argument. So the point is, such a proof shows that the sum must be finite and so on. And here, so you see together you have this, and therefore you have this sum. Now, clearly, that was the kind of the answer to our open point is, if you take a sufficiently finite set, the mu with the psi I will be a measure where you can also write it either as sum of the pieces of the measure, or you can make other brackets and say it's the sum of the bump functions multiplied with M. And if I look what happens if you add one bump function, another one, it's just locally constant 1, and at some point it stops going down. So it's really, if I multiply the mu with a sufficiently large plateau function, this is well-defined, a well-defined functional. I have a compactly supported functional, and therefore I have all the properties that we need, and therefore also the proof that we had before is okay. Okay, now I want to do the next thing, and this is what I call first the spline Quasi-Interpolation operator. That was the smooth version of this engineering picture that I have shown you. So I have shown you the smooth function, and I've shown you something which is not step function but was smooth, where I've moved these building blocks and they were adding up to something quite nice and close to this. So why do I call Quasi-Interpolation operator or spline type operator, or where's the word interpolation operator coming? Well, first statement, what happens if you want to plot a function in MATLAB? Kind of, you can say unfortunately or fortunately, because you have to understand what it's doing, you have to do it by hand. So you have to say, well, polynomial, how can I plot a piece of a polynomial? Then you have to design, maybe there are built-in routines now, but essentially you have to do it by your own. You have to say, well, I want to see the polynomial from -3 to +3. Then I want to have a fine resolution, so I have to sample the function at certain points. And then I have to call the plot, which is saying these points where I'm sampling and the values that I got from my function, and plot vector of sampling positions, vector of sampling points, and MATLAB will do a nice curve. And then you can zoom in and you say, well, it was a smooth curve. Maybe I wanted to plot a Gauss function. But actually what I see is a piecewise linear function. So what can MATLAB do? I mean, you can plot with stars or so. Then you will see 1 star, 1 star, 1 star or so. But the standard plotting routine is saying, evaluate this function, so kind of mark the point in the graph. And then you connect this with this and this with this. Now I do a reinterpretation and saying, this is exactly such a spline type operator. Now it's a spline of order 1, and it's an interpolating spline because they are kind of really having the right value. I'm saying, take the sampling point at the lattice, and then make a triangular function with this height. Then you go to the next sampling point, sample again, put another triangular function. Take another one. So we understand everything by taking just 2 points. There is a point value here and maybe a larger here. You're going here in a linear way from sampling value f of a to here, and you're going from 0 to f of b here. We're adding the two things. You're getting a straight line, and it's going from here to here. So piecewise linear interpolation is nothing else but an operator which is composed of 2 things. Sample the function and use the building blocks to put a shifted version of your element of your partition of unity in this thing. So you can also see, because we had discussion about spline type spaces, this is a very natural operator. It is not necessarily the best approximation operator. It's not necessarily interpolating. So if you think of cubic splines, you can have 3 routines, more or less, which we don't need here, but you can say, I want to have the best approximation by a cubic spline of the given function in the L2 sense. Then you have to replace the sample by the sample of a convolved version. So you have to modify the function a little bit, smooth it a little bit in the right way, and sample then. You can say, I want to have interpolation. Then it's not important that you have a partition of unity, but that you have a kind of Lagrange interpolator. So you compute the Lagrange interpolator. I would say you can take the basic B-spline and say, well, if I do this as a first approximation, but then I do a correction and a correction and a correction, that will eventually give you the interpolating spline. And they're all very similar, but for us, this interpolation is not important. Simplicity is much more important. So the important trick is, it is a combination of sampling and then applying a partition of unity. Now, what you will not find very surprising is that when you're doing this trick here, that you will get more and more better approximations. So the claim is this family of, let's first think of piecewise linear interpolations, is getting closer and closer to the original function as the widths of the triangles are going to 0. Sure enough, I mean, you look at the graphs and it's clear. Now, I told you I like nets very much. That's another case of nets. I mean, we have so many partitions. I've shown you very few ones. And we have only one measure of quality, which is how big they are, how wide they are. If you have piecewise linear, I mean, you have a narrow Gauss function, and you would be stupid enough to take a huge triangular function, you would probably stretch everything. Okay, now we're... Okay, the recording is on? Yeah, it is on. Yeah, okay. So should I continue? Yeah, for me it's no problem. Okay, so, but there's so many, and they are not sorted in, there's not a sequence or so. It's just saying in the very natural sense, whenever you're giving me any partition of unity, if it's fine enough for some measure delta, then the approximation error will be less than epsilon. Okay, how can we do it? And here we use the concept of oscillation. It's not really, I mean, the oscillation on an interval would say I have to pick up the maximal and the minimal value of a real valued function. We found out it's much more usable and also computable if you just take the deviation from the central value.
What is mod u tends to 0 there?
Sorry, u is the size of the diameter. So if you would say the support is an interval of length delta, that would mean delta goes to 0. So it kind of is the, once more I should remind you or I have not really explained it. Bounded uniform partition of unity, the segment, the U, refers to uniform in the sense of uniform size. So you are having triangular functions, maybe irregular, I mean, they're different positions, but the basis, the support size is controlled. And the controlling parameter is what I call the U, or the absolute value of psi. Maybe I should call it absolute value of size. In the sense of Riemann sums, it would be the size of the decomposition that the underlying. Yeah. And you refine more and more, and then that's so. But you're right, the U is not good here. Now the oscillation is just you look at some interval and you say, well, the function is deviating very much from the value in the center here or not. And of course, you can imagine that if you have a small interval, then uniform continuity already gives you that this will be less than epsilon, and that's more or less the definition of uniform continuity that we need. I don't even go, I think I skipped this style. What I think is you have to have the right terminology. The idea of how much oscillating you have is very natural. You write it down. Then to estimate and show that this oscillation goes to zero is more or less the definition of uniform continuity or so. But if you write down the details, then it's really, I think I like this separation. It's a pointwise separation. So whatever you do with these interpolating things, you can always control the difference between by the oscillation. So maybe we can look at this, the argument for this. And it's really just this line here. What is the value of the spline interpolation compared to the value of the x? Harmless trick. G of x is, of course, 1 times g of x. 1 times g of x is, of course, the sum over the psi I. So you're writing, okay, it's just the sum over the psi I. I was using already somewhere it's positive, so please ignore this here. I think it's better to think of non-negative. But it's over the g of xi minus g of x. Now, that can be quite big. I mean, g of xi is a given point and g of x is variable. No. You're working within the support of this here. So if you're working within the support of psi I, so kind of wherever this is non-zero, this x has to be very close to the xi. So at each center, you are only making use or using values which are within reach of size, this poo-poo. So of course you see then you have this term that this is one concrete pair of the values, and the difference is, and the trick is to make the x variable, not to look at each xi, but to view this as a function of xi, but it's the uniform continuity which tells you that the oscillation is controlling this, and therefore adding over all these psi I, suddenly they disappear. The sum of the psi is 1, and so you have sum over oscillation, the oscillation function summed over the psi I is just, of course, 1 times this. So this is the harmless trick to get this estimate, and because of uniform continuity, this goes to 0 uniformly, and you have approximation. Now, the next thing is a relatively harmless general functional analytic trick again. Maybe you think now of a situation that I am choosing a sequence of partitions of unity which go to which are finer and finer. So maybe you take a triangular partition of unity and then you compress it by the factors of 2, 8, and so on, and so it's getting more and more finer. So if you have a sequence of operators which are convergent in the strong operator topology, because this is exactly what we have here, you apply it to an individual function g from C0, and you see it's convergent. Then you can also look at the transpose operator, and it will have very similar properties. So now the next step is for us to look at the transpose of the operator. Yeah, that's this line here. Again, following the general recipe, if somebody has an operator, it's our SP psi, our spline quasi interpolation operator. It has an adjoint, and the adjoint maps the dual space into the dual space. So you can feed in a measure, a bounded measure, and you're getting another functional, another measure. So how can we understand it? We apply it to an f. And the general trick is, by definition of adjoint operators is, or transpose operators I should say here, it's duality in the Banach space sense, or it's a transpose operator, is take the original measure, which was the argument here, and apply it to the combination of f input function with the operator that you had on this original Banach space. So that's just the definition of the adjoint transpose operator. Then I'm saying, well, but this is mu is the sum of the psi I of the pieces. So that's how I was creating this operator. Maybe also you can check, that's another exercise, so to say, this is a sum which is norm convergent, not absolutely convergent. But it just says essentially, I mean, what happens if I take a big finite sum? I take all the partition of elements from here to here, then we're back to a plateau function. So therefore, if I take a sufficient long plateau function, it's fine. So it's norm convergent. And I would, of course, argue that the functional mu is a continuous function. So functional applied to an infinite sum is the same as the sum of the pieces. So one has to justify it, but it's easy to justify because of the situation. But now we have the situation that we have f applied to xi, and you see here we have some object which is abstractly defined, and we want to know what is the functional. So what is it doing on f? So we have to write this here as something which is acting on the f. And now comes the trick that, of course, f of xi is, I have not introduced it, but now I have to at least say it, a delta at x is such as the point evaluation. So we have now point evaluations at many points, and so I'm saying this is delta xi. We will discuss the discrete measures in more detail anyway or so, but that's a way of rewriting it. And so from this formula, and knowing that the SP psi operators are good operators, we can argue that probably these operators are good kind of approximations to the measure that we had originally. And so first we define, given a partition of unity, we define the discretization operator by just taking what is applied to the f. So it's something like this here. And what is it in principle? It's a sum of discrete point measures. What are the amplitudes? Well, we have seen that the sum of these local pieces is absolutely convergent. This is unfortunately not exactly the same. One has to have a little bit of discussion to show that, because the sum of the pieces measured, so that would be mu times psi I measured. And now we're applying mu on psi I. And one has to use a small one-line argument or so. But essentially, one can already expect this will be a sequence of coefficients which will be absolutely convergent, so an L1 sequence. And then you have this sum. So somehow you have an infinite discrete sum of measures. Now, I'm not sure, I think it's a bit dark. I will just mention that, maybe show pictures for the next session or so, how one can visualize it using the idea of probability measures. So the standard way of working with probability measures, or one natural way, is to think of a probability measure through the distribution function. So if somebody is telling you he has a normally distributed function, you probably think of the distribution function being very close to 0, going up, and then reaching the level 1. So you would say, this is telling you, given such a normal distribution, what is the probability that this random variable takes values between -infinity to some alpha? And if somebody is interested to know what can you say about the probability that you're in the interval from alpha to beta, then you would say, well, it's having the value, that value here, and at beta later it has a slightly larger value, so you take the difference of these values or so. So short summary, if you have a nice integrable function, an L1 function, or bump function, which is a probability density, you have an integral going up like this. Now, as an exercise, what would be a discrete measure? How would a distribution of a discrete measure look like? First of all, if I'm kind of standing at 0, what would be the distribution function at 0? Well, a set interval minus infinity to minus 3 would not contain the point. You would have measure 0. Up to minus epsilon would be nothing. From that point on, it would be 100%. So I don't care about this single point. It would be a step function going up. If I put a Dirac here and let's say 2 Dirac here, it would be a step function with step height 1, going over to this point, jumping 2 more, and then 3. So of course, maybe you normalize if you want to have a probability measure or so. So then the question is, what is a natural concept of approximation of a measure, now really thought as a probability measure, mu, by a discrete measure? And that's again a question where you can ask people who are not very deep education in mathematics, how would you approximate such a smooth ramp function with step function? And so you would say, probably I'm following the ramp. But I have told you what is the height of the jump. That's exactly the probability of this here. So we're essentially back to my story about histogram. If I have not the random variable in an abstract way, but I have a nice histogram, what I could do as an approximate random variable distribution function for the discrete measure would be a step function. I would jump. Now it's the question whether I take maybe the midpoint of the bin or so to do the jump, or some point interior or so. But that's exactly what I'm doing here. I'm saying I'm jumping at the position xi. And if I'm a bit generous, I mean, it doesn't have to be exactly the midpoint. It has to be some point such that the support fits into a small interval around it. So I'm putting the jumps of the right height, and this is telling me how much height I have to do. Now, if you think now of the same thing with 2D, somebody would give you a landscape or so. Now, a good idea of thinking of the landscape is to say, well, you have a black and white image, and the gray value is the amplitude or so. And we're talking about analog photography, so you have a really continuous function. Now, I would say, what you're doing when you take a picture with your digital camera is exactly this here. You're taking over every pixel some local average. And if you think what the camera is doing is maybe, I mean, practically, I would say, physically, these chips are not really covering everything. They are even a little bit less finer. So I would say what one could probably do, one could say it is not even if the function, if the measure is nice, you might even take something smaller because everything is blurred anyway or so. But roughly speaking, that's, so to say, the pixel value at the given pixel, which is the average of all the photons in that quadrant. And then you have, say, that's actually quite nice. If you look at it from the distance, it's fine. So we will see that if you use it as a convolution, that will be the trick of the story. If you use this discrete measure as a convolution operator, it will be almost the same as the convolution operator itself. And we always talk about convolution being a smearing operator. It's a kind of sum of translates, and we go to the limit. And that makes this idea precise. So I'm not sure about the timing because I don't see a watch now, but I think we should come to an end now. Yeah. So I think the very quick picture is this is a strange partition of unity operator. Then in the strong operator topology, you are having an approximation. So if you know what the input is or what the smoothness of the input is, we will get an approximation. And that means the convolution operators coming from discrete measures, that was also a question before, are approximating in the strong operator topology all the convolution operator, all the translation invariant systems. Because these discrete measures are commutative, that's because the group law is commutative. You will see, I mean, I didn't discuss, that's maybe an important point. What is the convolution with a delta? This is, of course, a shift operator. So we should do this discussion also. So because the convolution of Diracs is commutative, because shift operators are commutative, we can push it to the limit, and then we're at the stage where we're saying, okay, now this family of systems is a commutative algebra, which again for engineers is maybe something surprising because they have these boxes. And I mean, as we have heard, we are within the algebra of operators. This is a non-commutative algebra. So why are they allowed to take the box and change the order of the boxes? I mean, it's absolutely not clear. But if you know it's a commutative subalgebra, then you know the order of operators doesn't matter. And maybe one order is more convenient than the other or so, or you're combining two of them to get some, I don't know, pre-filtering or so. Okay, thank you very much for now, and we will continue on Monday then. Thank you.